Hello everyone. Today I'm going to be talking to you guys about the Earth's atmosphere, its makeup, and the parts of it. But before I begin, I want to give you guys something to think about. If you ever look up at the clear blue sky, it looks very two-dimensional. It doesn't look like it has any depth to it. It doesn't look like it has a beginning or the end, but the atmosphere actually does have a beginning and an end, and actually begins where you are right now, and it goes up well above the Earth's surface. So, the atmosphere is made up of gas molecules, which are densely packed near the surface, and they go up to about 300 miles above the Earth's surface. And now we'll talk about what it's made of. At first, it was thought to have consisted of mostly hydrogen and helium, most of which diffused into space over billions of years through atmospheric leakage. Carbon, nitrogen, sulfur, oxygen, and other elements that can normally be found in the atmosphere were added from volcanic emissions. Algae, among other early plants, contributed to the oxygen on the planet, so we can thank those early oxygen producing organisms for the oxygen that we have today. And if you look at this little pie chart, this is pure air, which is around 78% nitrogen, 21% oxygen, and the rest is made up of other gases such as argon, helium, methane, neon, and carbon dioxide. Now, these are the layers of the atmosphere that we'll be talking about in depth. Down here, the first layer, the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere, all the way up here. So, let's talk in depth about the troposphere. Atmospheric layers are determined by the absorption of solar energy, and that's what divides the layers. So, the troposphere is where you live. The atmosphere begins where you are standing. It's a very dynamic layer where the weather occurs, and it stretches to about 7 miles when it's above the equator and 4 miles above the poles. If you look at the structure of the atmosphere and the magnetic field, it actually looks like it begins from the poles and wraps around. So the atmosphere is actually thinner near the poles, which is why we have to be careful what we put into it, because Arctic ecology is very much exposed. And although this is such a small layer, 75% of the total mass of the atmosphere is in the troposphere, right where you are. And that happens because gravity holds the air molecules close to Earth's surface. And the Earth's surface produces heat, which is why even though this is the farthest layer from the sun, we still have heat because our planet absorbs sunlight and transfers it to heat by air that rises up through a process called convection. The troposphere is warm compared to the stratosphere, but it's definitely much cooler compared to the thermosphere. Now, between the troposphere and the stratosphere, there's something called the tropopause. And right above the tropopause is the ozone layer. Stratospheric ozone absorbs a lot of solar energy, which makes it warmer than the troposphere in some parts. The stratosphere is thinner and contains much more ozone and almost no water vapor. It's very dry. Now, we need UV absorption to happen in the ozone because it helps us there. At ground level, ozone is actually an air pollutant and can cause damage to life on Earth, and it's essential that ozone stays where it is right now. And thinning of the ozone can increase cancer rates and cause damage to life on Earth, which is why we need to regulate and restrict the pollutants such as chlorofluorocarbons right up here. They used to be used in air conditioners. They were banned in recent decades. And these chemicals can stay in the atmosphere for a while because there's no vertical convection like in the troposphere. So the air flows horizontally in the stratosphere, so material will not rise out of the layer. It'll take a while to do so. Even volcanic eruptions can shoot debris that get caught in the atmosphere and have an effect on climate. Similar to volcanic winter, when all the volcanic emissions will block out heat from the sun. In depth to the stratosphere now. The stratosphere begins at around 10 miles and ends 31 miles above the surface. It's much more stable and cooler until the upper altitudes, and the air flows horizontally. There's no vertical convection. Now, the lower altitudes of the stratosphere are where we can find some airplanes, which situate themselves in this layer to avoid turbulence. There aren't that many clouds in this layer because of how dry it is, but if you've ever been on an airplane, you won't see many clouds directly across from you. If you look at this picture from an airplane window, most of the clouds will be below you. I mean, sometimes you see these giant clouds like bulging out from that layer, but for the most part they're all below you. The clouds that you may see in the wintertime are called polostratospheric clouds, and these could actually speed up holes in the ozone layer by catalyzing chemical reactions that destroy ozone. Now, luckily for us, there are not that many of them. There are very few. It's quite rare to see, and that's good because it will speed up ozone depletion. The actual beginning of this layer depends on what season it is. It's lower in the winter and higher in the summer due to the expansion of the troposphere by sunlight. So up here in the northern hemisphere, we're approaching summer, so the stratosphere will be higher. Now, between the stratosphere and the mesosphere is something called the stratopause. Now, the mesosphere is very interesting. It shows a decrease in temperatures, and it's the coldest part of the atmosphere in the upper sections. This starts around 32 miles up to 53 miles above the Earth's surface. And there are actually clouds that form here called noctilucent clouds. They have some sort of frozen water structure to them, and there's a mysterious lightning phenomenon down here in the bottom left called sprites. It's hard to study the mesosphere really because of actually getting there and using the tools we have to get the information. So there's still much more we have to know about it. And this is the layer where most meteorites burn up. Now, between the mesosphere and the thermosphere is the mesopause. Now, the thermosphere starts around 56 miles. The lower thermosphere contains very high temperatures which decrease and level off as it goes on. Solar activity and the time of day influence the temperature here. It's not easy to pinpoint exactly where this layer ends because it's so lightly dense that it's basically outer space. And this is the layer where the International Space Station and the shuttle can be found. Whenever you see pictures of them in orbit, it looks like it's in outer space, but it's not. It's still very well in the atmosphere, held by Earth's gravity. Now, the ionosphere is part of this layer. It's not really its own layer, but solar energy can break apart molecules to the point where in this layer, there are electrons flying and molecules are losing and gaining electrons, and that's where you could see the northern or southern lights, the aurora borealis or the aurora australis. Now, as I was talking about a little in the troposphere, the magnetic field of Earth, it's weaker near the poles, where you are more likely to see these charged particles colliding with atmospheric particles showing up as auroras because they give off light photons producing beautiful waves of high energy. So you can see here, near the poles, the magnetic field is weaker and it wraps around. So when the charged particles come towards Earth and you see the northern lights, you're more likely to see them up here. However, we actually had a northern light event in New Jersey. Couldn't see it because it was too rainy that day, but the strength of the solar flare was so huge you could see it in the more southern latitudes. Not just near the poles, it all depends on the energy of the solar flare. Now, above the thermopause is the final layer, which is the exosphere. It's a very thin layer of the remaining atmosphere which leads into the vacuum of outer space. The bottom part of this is called the exobase, and where this layer starts and ends, of course, like the other layers, depends on solar activity. The thermosphere's atmosphere can be raised by X-rays and UV rays during sunspot maximum, and during sunspot minimum, the thermosphere is smaller. Now, it's debated whether or not this is actually a part of the atmosphere, but it's worth talking about because it's there. And actually, many satellites will orbit here above the ISS and the shuttle orbit. This is a rough computer-generated image of a satellite map. There are a ton of satellites orbiting Earth like you wouldn't even know. So, I hope this has been a rough introduction to the atmosphere for you. Thank you for watching, of course, and I hope this allows you to look at the atmosphere with a more 3D structure. Thank you and goodbye.